predicting reactant and product amounts. Now this is all theoretical, but it's really useful because you could be the guy who is making a beer kit or cleaning supplies or a colon bowel movement product. The point is that these commercial products out on the marketplace, they have a lot of different ingredients, a lot of different reactants. Well, what if one of those reactants is really expensive? Well, you want to use up all that reactant in producing your commercial product, right? And you don't really care about all the other reactants. Or you might want to know, okay, just how much of this particular compound is going to be produced in this reaction once they're all mixed together, because you need a certain amount for your product to be viable. So these calculations are really important and really, really useful. So let's start out just by reading a chemical equation. So here's a chemical reaction. We have reactants going to products, but how do you read it? These are mole ratios. Do you remember these are the stoichiometric coefficients? So how we read it is you would read it as 2 moles of dinitrogen pentoxide react to produce 4 moles of nitrogen dioxide and 1 mole of oxygen. Now this is an important point because these are mole ratios. These stoichiometric coefficients are mole ratios, not gram ratios. They're mole ratios. They're actually saying that 2 molecules at the molecular level, 2 molecules of this dinitrogen pentoxide are producing 4 molecules of nitrogen dioxide and 1 molecule of oxygen. Well, we could just as well say 2 dozen dinitrogen pentoxide molecules produces 4 dozen nitrogen dioxide molecules and 1 dozen oxygen molecules. But a dozen's not enough, remember? So these molecules are very small, so we need to work with huge, huge units of them. A mole, 6.022 times 10 to the 23rd. So 2 moles of dinitrogen pentoxide produces 4 moles of nitrogen dioxide and 1 mole of oxygen, okay? Now what we're going to use these chemical equations to convert from one compound to another, and we call that mole bridges. And they're just ratios that we get from the chemical equation. So what are a bunch? We could say there's 2 moles of dinitrogen pentoxide for every 4 moles of nitrogen dioxide. So all I'm doing is taking these ratios, these mole ratios. What else could I pick out? I could pick out 2 moles of dinitrogen pentoxide for every 1 mole of oxygen. Or I could say 4 moles of nitrogen dioxide for every 1 mole of oxygen. And there's 3 more ratios. Just flip these. Just flip them. Right? For example, 4 moles of nitrogen dioxide for every 2 moles of dinitrogen pentoxide. So you can just flip all these ratios. You'd have 3 more. So there's a total of 6 mole bridges that we have. So how do you use these mole bridges? If 4 moles of dinitrogen pentoxide react, how many moles of NO2 are formed? See what we mean by mole bridge? We're changing the compound. We're going from one compound to another compound. And how do you do that? Mole bridge. So always start with the measurement. 4 moles of dinitrogen pentoxide. Make your ratio. Moles of dinitrogen pentoxide has to be in the denominator. Otherwise it won't cancel. So what ratio am I after? I'm after moles of dinitrogen pentoxide to moles of nitrogen dioxide. What's the ratio? Dinitrogen pentoxide is a 2, NO2 is a 4. So 16 divided by 2 would be 8. What if we have 3 moles of dinitrogen pentoxide and we want to know how many grams of NO2 are formed? So again, we're going from one compound to another, so we need to use the mole bridge first, and then to go from moles to grams, we'll use molar mass. Check this out. We'll start with the 3 moles of dinitrogen pentoxide. Right? The moles of dinitrogen pentoxide has to cancel, so that's in the bottom. We want to convert to moles of NO2 because we can't go to grams of NO2 right away. So this will be our mole bridge. Then moles of nitrogen dioxide has to be in the denominator. Grams nitrogen dioxide, molar mass. So now we just put in our numbers. So now we just put in our numbers. The mole ratio of nitrogen dioxide to nitrogen dioxide to dinitrogen pentoxide, 4:2. And the molar mass of nitrogen dioxide, and 1 mole of nitrogen dioxide, right? Nitrogen is about 14.01 plus oxygen, each one is 16. 16 times 2, about 46.01. So everything on top multiply, bottom divide. 3 times 4 divide by 2 times 46.01. About 276. Because all of my units canceled except grams of nitrogen dioxide. And they didn't specify sig figs, so we're not really even worrying about those anymore. Just report your answer to 3 or 4 digits and you'll be fine. The last one here, we're starting with 2.8 grams of nitrogen pentoxide. How many grams of NO2, in theory, should be formed? So again, we're going from one compound to another. We need a mole bridge, right? And then we'll use molar mass again. But if we're going to use the mole bridge, we're going to have to get this in moles first. So always start out with your measurement. All right. So first we'll need to get it into moles of dinitrogen pentoxide, and that's molar mass. Now we're in moles. We'll use the mole bridge to get it into the right compound, and that's nitrogen dioxide. Then they want the answer in grams, so let's use molar mass to get back to grams. Now we said the molar mass of nitrogen dioxide is 46.01, and NO2 to N2O5 is a ratio of 4:2. All we need is the molar mass of dinitrogen pentoxide. So nitrogen is like 14.01 times 2 plus 5 times 16, about 108. So everything on top multiply, bottom divide. 2.8 divide by 108 times 4 divide by 2 times 46.01. I get about 2.39 grams of nitrogen dioxide. Here's another one. Nitric acid is manufactured by the Ostwald process, in which nitrogen dioxide reacts with water. How many grams of nitrogen dioxide are required to produce 7.5 grams of nitric acid? So again, we're going from one compound to another. We need a mole bridge. Got it. You have the chemical reaction. Always start with the measurement. So we're going to start with 7.50 grams of nitric acid. We're going to convert and stop when we finally hit grams of nitrogen dioxide. And then we'll have our answer. So since we're going from one compound to the other, we have to use the mole bridge. That means we have to be in moles. So get the molar mass first of nitric acid. And since we're in moles, now we're ready for the mole bridge. And we want to end up in nitrogen dioxide, so we need that on top. And they want the answer in grams, so I have to go all the way to grams using molar mass of nitrogen dioxide. So what's the molar mass of nitric acid? 1.01 plus 14.01 plus 3 times 16, about 63.02. And I have 3 moles of nitrogen dioxide for every 2 moles of nitric acid. And the molar mass of nitrogen dioxide is 46.01. So now what do we get? 7.5 divided by 63.02 times 3 divided by 2 times 46.01, about 8.21. So if 7.5 grams of nitric acid react, in theory, 8.21 grams of nitrogen dioxide will be produced. Acrylonitrile is the starting material for the production of a kind of synthetic fiber. It can be made from propylene by reaction with nitric oxide. How many grams of acrylonitrile are obtained from 452 kilograms of propylene and excess NO? So we have 452 kilograms of this stuff. That's a lot. And they want to know how many grams of acrylonitrile we're going to end up with. So what's this excess NO have to do with anything? Well, what they're saying here, excess means extra, right? So that means you have to have way too much of this stuff. You have way too much. That way, all of this will react. All of that will react. And you'll have a bunch of this nitrogen oxide left over. Fine, we don't care. Just all of this acrylonitrile is reacting. And that's how it always is. Right? That's how these problems need to be. You need to have excess other reactant. Otherwise, all of this wouldn't react in the first place. Make sense? So let's try this. Start with the measurement. 452 kilograms of propylene, C3H6. We're going to convert and stop converting when we end up with grams of acrylonitrile. Stop there, and we'll have our answer. Okay, so let's just write out the units first. That seems to help me anyway. So I know that kilograms of C3H6 has to be on the denominator. I'm going to need to convert to grams so I can use molar mass, so I can get into moles, so I can use my mole bridge. So let's do that first. Kilograms to grams of propylene. So that'll be the first step. Now I'm in grams, so I'm ready for molar mass of propylene. And then once I have moles, now I'm ready for mole bridge. And I'm trying to end up here in moles of C3H3N. Last step would be the molar mass. And moles has to be in the denominator. So how many grams in a kilogram? 1,000. In 1 mole, I have 3 times 12.01 plus 6 times 1.01 about 42.09. And my ratio is 4 to 4. My molar mass, 12.01 times 3 plus 3 times 1.01 plus nitrogen, 14.01, about 53.07. Okay, 452 times 1,000, divide by 42.09 times 53.07. About 5.7 times 10 to the 245 grams of acrylonitrile. How many grams of nitrogen monoxide must react if 12.23 grams of propylene react? So start with the measurement. So I'm just going to write out my units. Molar mass first, mole bridge next, wrap up with molar mass. So the molar mass of propylene, we did that already, it's 42.09. The mole bridge, we have 6 moles of nitrogen monoxide for every 4 moles of propylene. And the molar mass, in 1 mole of nitrogen monoxide, I have 14.01 plus 16, about 30.01 grams. So 12.23 divided by 42.09 times 6 divided by 4 times 30.01, about 13.1. So in theory, I should get 13.1 grams of nitrogen monoxide if all of that 12.23 grams of propylene reacts. If 4.2 grams of water are produced, how many grams of nitrogen must also be produced? So I have 4.2 grams of water. I need to get that into moles first so I can use my mole bridge. Then I'm ready for the mole bridge, and I want to go from moles of water. I want to end up in nitrogen. Then the molar mass of nitrogen, because they want the final answer in grams of nitrogen. So in 1 mole of water, I've got about 18 grams of water. And I've got 6 moles of water for every 1 mole of nitrogen. And in a mole of nitrogen, I've got 28.02 grams. 4.2 divide by 18 divide by 6 times 28.02, about 1.08, 1.1. Okay, here we're going to start with the measurement, end up in grams of propylene. So 0.03 moles and we want to end up in grams of this compound. Okay, we're already in moles, so we're ready for the mole bridge. It's kind of nice. We want to end up in moles of C3H6. They want the answer in grams, so we better go all the way to use molar mass. So we have 4 of these for every 4 of those. And in a mole, we have 12.01 times 3 plus 6 times 1.01, 42.09, sounds familiar. Okay, 0.03 times 42.09, about 1.26, about 1.3. Again, we're not really worried about sig figs. If we were, we'd just report our answer to 1 sig fig, use the initial measurement. Okay, this next one. Let's clean this up a little bit. If 23.2 grams of NO, if 23.2 grams of this compound is mixed with 24 grams of the other reactant, how many grams of this product are we going to get? So one of these, see, this is the type of problem we're going to handle in the next class period. So we're not going to do it here. But do you see the problem? Which one of these is going to all react first? Is it going to be this one, or is it going to be this one? One of them is going to react up first. We don't know which one. But once we do know, we'll use it to get our final answer. So we'll worry about that the next class period. But you can see what's coming up. So tungsten metal is used to make some bulb filaments, and that metal is produced through this reaction. How many grams of tungsten can be obtained from this many kilograms of hydrogen with excess tungsten oxide? Okay, so that means this is all going to react first. How much tungsten can you get out of that? So we want to stop at grams of tungsten. We're in kilograms of hydrogen, so we need to get to grams of hydrogen. Then once we're in grams of hydrogen, we can get into moles. Then we're ready for our mole bridge. And moles of hydrogen has to be in the bottom. We're after tungsten. And they want grams of tungsten, so we're going to have to use the molar mass of that stuff. So in 1 kilogram, we have 1,000 grams. In 1 mole of hydrogen, we have 2.02 grams of hydrogen. And we have 1 mole of tungsten for every 3 moles of hydrogen. And the molar mass of tungsten is 183.84. 4.81 times 1,000. Divide by 2.02, divide by 3, times 183.84, about 1.46 times 10 to the 5th grams of tungsten. So in theory, that's how much tungsten will be produced. So these problems of predicting reactant and product amounts, they're all really have the same game plan. You always start with the measurement, right? And then you're going to use a mole bridge from a chemical reaction to convert from one compound to whatever compound you want. And if you ever have to go from grams to moles or moles to grams, just make sure you use molar mass. And all your units need to cancel out until you end up with the units you want.